If I could issue a warning to help you avoid problems on the exam. I'm an old man, I've been doing this a long time. And what I see is that over and over again, people try to find the frequencies of different harmonics using these formulas. That are in the formula dump. Now, they weren't in my original version of this chapter 15. They were added because a lot of people like to use them. My experience, again as an old man that's seen this go down a lot, is that almost everyone that uses those formulas gets the wrong answer. And that's because they use the wrong formula or they use the wrong value for n, and it's a mess. And so I would encourage you to just forget about those. Just forget about those. And use those two formulas that are over on the right. Okay? You can always use the wave equation. And that's going to work for every harmonic. I don't have to worry about the value of n. Okay? And it's also going to work whether you've got the n's the same or the n's different. So you don't have to worry about which equation do you use. You always use that one. Now, I can't draw a frequency, but I can draw a wavelength. And so, for example, in this problem 10, you're told that the tube is 2 meters long. And I've got the second harmonic going on. Well, if you use those fancy formulas that get you into trouble, you'd have to worry about which one to use, which value of n. But here I just draw the picture and I say, hey, how big is my wavelength? Well, it takes 2 footballs to make a wavelength. I got 2 footballs in this 2 meter long tube. My wavelength must be 2 meters. It's a sound wave, so this is 343 meters per second is equal to the frequency times 2 meters, and I get a frequency of 171.5 hertz, or 343 over 2. Now, if you have a hard time seeing that the wavelength is 2 meters, use that second equation over on the right board. The number of footballs times lambda over 2 is equal to the length of the system. Well, here I've got 2 footballs times lambda over 2 is equal to the length of the pipe is 2 meters. Well, that gives me lambda is equal to 2 meters. I don't even have to know which lambda it is, that it's the second harmonic. I'm still going to get the right answer for the frequency. Okay? Now, that's not the part that got this voted off the island. You're told that while these particles in this tube are sloshing back and forth, remember you in the bathtub scooching back and forth, making the splashing, we take a snapshot. And this point F at the antinode has a big displacement to the right when we took the snapshot. Now, this football representation is a particularly lousy representation. There's nothing that's going this way in this tube. The particles are rushing together to crunch a node or rushing away to desert a node. And each node, well, let's talk about where the node is. The node's not just right there. That's what this football representation would lead you to believe. But in this tube, every particle in this whole layer of gas is at a node. So this point, that particle would not be moving. This particle would not be moving. This particle would not be moving. That particle would not be moving. Likewise, over here, D is not moving. But neither is this point or that point or this point or that point. Now, each of these node areas are being crunched and then deserted, and then crunched and then deserted. That's what this sloshing is, back and forth, back and forth. And that's what causes the sound that comes to our ear. Now, every particle in one football has to be going the same direction. So if F is going to the right when we took the picture, so is E. The only thing the football's good for is telling me how far it's displaced from equilibrium. If the football's narrow, it's not very far. If it's fat, I'm at an antinode and it's big. Now, when one football's going to the right, the neighbor's going to the left, because that means that this node is being, deserted. So that means this would be going like that, these guys would be going like that, but also I'd have particles over here that would be going like that. I'd have particles over here that would be going like that. This particle would be going like that and like that. Now, if this node is being deserted when we took the picture, this one's being crunched from both sides. And the closer I am to an antinode, the bigger the displacement. Okay? Now, if I wait half a period, okay, all the arrows would be reversed. Okay? So this one's being crunched when we took the picture, but a half period later it would be deserted. This one's being deserted when we took the picture, a half period later it would be crunched. See if your neighbor understands the sloshing that's going on in that tube.
So we know we're told that have the rings of power means that this node is being reversed. So that in that node also.
Okay. Like to talk about this exam question. I put it on an exam many years ago, thinking that it would be a gimme, that everyone would get it right, that it would be very easy. The question is, you can tune the frequency of a guitar string without changing its length. To tune a flute, however, you have to slightly adjust the length of the tube. How do you account for this difference? Now, as we were grading that night, we found that almost no one got this correct. And the most common wrong answer that we got over and over again was this: flutes don't have strings. If they had them, we would use them. But they don't have them. More's the pity. Okay? That's not the answer we were looking for. Okay? But it is hard to argue with. Flutes don't have strings. This is what we were looking for. Regardless of whether the wave is a transverse wave on a guitar string or a longitudinal wave in a flute, it has to obey the wave equation. Now, tuning means changing the frequency, making the frequency bigger or higher or smaller, lower, changing the pitch. Now, we have to ask ourselves, in that equation, what can we do to change F? Well, on a guitar string, if I don't put my finger on one of these frets, if I don't push down on the string is fixed in length. And the first harmonic is going to be twice the length of the string. And so there's nothing I can do about that. It is what it is. So that means the only way I can change the frequency is to change the speed of waves on that string. Now, for a transverse pulse or wave, we have this formula. Now, this mass density is just how much mass you have per unit of length on that string. And when an E string comes out of the factory, that's fixed. That's already set in stone. So the only way you can change the speed is by tightening the string. That's going to make the speed faster. That's going to make the frequency higher. If I loosen the string, that's going to slow down the speed of waves. That's going to make the frequency lower. On the other hand, flutes don't got strings. So if I want to change that frequency, I ask myself, what can I change in that equation? Well, these are sound waves that are going back and forth, and so the speed is constant. It's 343 meters per second. Now, I feel silly saying that to a bunch of people who live in Bozeman, Montana. I mean, I had a son who was in high school marching band, and then, tune up their instruments in the gymnasium and march out onto the field and out of tune, okay? Why? Because it was room temperature in the gymnasium. It was 40 below out on the field, okay? That's just part of living here. But given the fact that you stay inside the gymnasium, you can't change the speed of sound, okay, without turning the thermostat. And that means I need to change the wavelength in order to change the frequency. The smaller I make the wavelength, the higher the frequency. Now let's understand what that means. If this represents my flute, open at both ends, and I want to tune that, I want to make it a different frequency. Do I want to lengthen the tube so that I can fit more footballs, or do I want to lengthen the tube so I can get bigger footballs? Which is it? Talk to your neighbor. I want more footballs or bigger footballs?
Change the tune of I always do that. I think that's a coincidence. I think you change the length of the tube because...
Okay.
Well, what's the difference?
I hope everyone said you wanted bigger footballs. Look at this equation. The speed, it's a sound wave. The speed is fixed at 343. The frequency times the wavelength, but a wavelength is 2 footballs. So, if I have the same size footballs, I've got the same frequency. Listen to that again. If 2 instruments have the same size footballs, they are playing the same note. Okay? This instrument and this instrument have the same size football. They are playing exactly the same frequency, the same note. That one's playing it as the first harmonic of its instrument. This one is playing it as the second harmonic of its instrument. But it's the same note. Okay? In your homework, you had 2 tubes. A tube A and a tube B. And tube A was open at both ends and tube B was closed at one end. And you were told that they were playing the same first harmonic. Well, the first harmonic here looks like that, and the first harmonic there looks like that. If they have the same first harmonic, they have the same size football. Now, you were told in that problem that tube B, the one that was closed, had a length of 0.4 meters. Well, that's the size of half a football, if I'm playing that note. And so this would also be 0.4 meters, which means that A has to have a length of 0.8 meters. It would have to be twice as long. It's got the same note, same size footballs, it's just got twice as many footballs. Okay? Now, we don't usually want to double the length of our footballs. Usually when we're tuning, we're just trying to make the frequency a little different. And so we would just lengthen the tube a little bit or shorten it a little bit so that the frequency would change a little bit. See if your neighbor understands why flutes don't have strings. Okay. If you would please turn that exam preparation sheet over. I have an old exam question that turned out to be a little bit too hard. I gave this problem 22 years ago and it turned out to be way too hard. I got to tell you folks, back in the day when I was young and skinny, I didn't have much of a clue as to what a good question was on an exam. And the average on most of our exams were down around 40%. It was a terrible time. It was the black years. And people come up to me in Bozeman, oh, I had your class. As when? Oh, 20 years ago. Oh, I'm so sorry. I'm so sorry. So it could be worse, people. It could be worse. Now, because this problem was difficult, it turns out to be a wonderful teaching problem. And so that's what we're going to do, and we'll be grateful that it's not on our exam. What we have is a column of air that is 4 1/4 meters long. We have a cylinder that's 5 meters long, and we adjust the length of the air column by putting water in the bottom. And we just have 3/4 of a meter of water in that bottom there. Now the first part of this problem asks us to find the fundamental frequency F1. Now folks, I cooked all the numbers in this problem so that they would be easy, so that they would work out really, really nice if we assume it's a little bit cold today. Okay? So what we're going to do in this problem is instead of taking 343 meters per second for the speed of sound, we're going to round that down to 340. So in this problem, let V is equal to 340 meters per second, the sound speed. Okay, so it's not room temperature. Now, when I saw people flailing on this problem, struggling with really hard, messy mathematics, I made an announcement in the class, make this approximation, and that helped a little, but still people had trouble. So, with your neighbor, find the fundamental frequency of that tube. Okay. Let's do this the way I encourage you to do it. Let's use the wave equation. And since we can't draw a frequency, we'll draw a wavelength. This bottom where the water is has to be a node because the molecules can't move that way. It's a barrier. The open end has to be an antinode. And the fundamental wavelength is the longest wavelength that will fit. And it's the one that goes straight from a node to an antinode, like that. Now, that's only half a football. It takes 2 footballs to be a wavelength. And so that means a wavelength, my lambda, is 4 times the length of that half football. Now, if that didn't speak to your soul, just use this equation. Number of footballs times lambda over 2 is equal to the length of the system. I've got half a football there times lambda over 2 is equal to 4.25 meters. That means lambda is equal to 4 times 4.25 meters, or 17 meters. I bring that up here, and I say 340 meters per second is equal to F, it's the first harmonic, times 17 meters. That gives me F1 is equal to 20 hertz. See if your neighbor got 20 hertz. Okay. So first we found the fundamental wavelength. We drew a picture of it. We recognized that it was 1/4 of a wavelength. So we multiplied the length of the air column by 4, got 17 meters, and that's what got us the 20 hertz. Now, if I were to just blow air across the top of this air column, making white noise, 20 hertz is a sound that would resonate. And we might or might not hear that because it's right on the edge of human hearing. But still, that would resonate in the tube. What that means is that if I brought a tuning fork that was 20 hertz, I could excite the fundamental. Now, if I brought a tuning fork that was 40 hertz, would I get an echo? Would I get a booming sound out of that air column?
No.
Why?
It's not the curve.
Yeah, only the odd harmonics are going to resonate with this system. So this would not, but if I did 60 hertz, it would resonate, and it would resonate with the third harmonic, and that would then look like that. Now, in the next part of the problem, we take a tuning fork that has a frequency of 340 hertz, and we ask which harmonic is going to resonate with that tuning fork. Which harmonic is going to resonate with that tuning fork? Pretty easy.
No.
The nth harmonic is always n times the fundamental, or the first harmonic. In this case, we're exciting the nth harmonic at 340 hertz. This air column has to resonate or sing at the same frequency at which it's being tickled or perturbed. That's going to be 340 hertz. That's going to be equal to n times the fundamental of 20 hertz, and that gives me an n value of 17. It's the 17th harmonic. Now that's what the third harmonic looks like. What would the 17th harmonic look like? How would you draw that? How many footballs would be in the tube? Talk to your neighbor. What would the 17th harmonic look like?
The third harmonic.
Half of what the harmonic is.
17 plus 3
Can anybody help me out? 8.5. Excellent. How did you get that? Perfect. Okay. If the third harmonic has 3 half footballs, and the fifth harmonic has 5 half footballs, and the 7th harmonic has 7 half footballs, then the 17th harmonic has 17 half footballs. Well, 17 half footballs is 8.5 footballs. And so what it would look like is 8 footballs and a half at the top. Now there's another one. I think that's the best way to get it. There's another way to do it. And that is to find out how big your footballs are. Okay? If I use that wave equation again, well now, E equals F lambda, I'm doing it for the 17th harmonic. This is 340 meters per second. This is 340 hertz. That makes lambda 17 easy to calculate. It's 1 meter. But that's 2 footballs. A wavelength is 2 footballs. And so that means 1 football is half a meter. And so the other way to do it is just ask yourself, how many half meters do I have in 4 1/4 meters? 8.5. 8.5.
Did you just set up a proportion?
You could do that too. Set up a proportional. That's all I'm doing is proportional reasoning. Yeah? Now that's going to look like that. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 8.5. Now folks, the reason this echoes, the reason that this gives me a booming sound is because it fits the boundary conditions. Namely, a node at this closed end and an antinode at the open end. Now, if I lower the water level a little bit, that goes away. These footballs are tied to that frequency. Okay? And so if I lower this water just a little bit, that frequency no longer resonates with this air column. The echo goes away. But if I keep lowering the water, I can lower it to a point where the echo comes back strong as ever. And again, it sounds like it's the same echo. It's still being played at 340 hertz. I still hear the same note that I heard before. How far would I have to lower the water in order to have that echo come back again?
0.5 meters.
What's that?
0.5 meters.
0.5 meters, right, because I have to fit another football in there. So I'm going to have to lower my water level half a meter. But now I'm not playing the 17th harmonic anymore. Which harmonic am I playing now?
19.
The 19th. Well, wait a minute. If it's still 340 hertz, how can it be the 19th harmonic and the 17th harmonic? Well, by dropping this level of the water, I change the fundamental. And so now the fundamental is not 20 hertz anymore. It's something lower than 20 hertz. And now 19 times the new fundamental is 340. Whereas it used to be 17 times 20 gave me the 340. Okay? You can even figure out what the new fundamental was really, really easy just by using the wave equation. Do this for the 19th harmonic. 19th harmonic. Well, no, I don't want to use this equation. I want to use Fn is equal to Nf1. If this is still 340 hertz, and this is the 19th harmonic, I can solve for F1. And I'll get something smaller than 20. Check that your neighbor's on the bus with this problem and express your gratitude that it's not on your exam.
No, because water bottles on my plate that I left in the it's okay. I didn't. You said, am I here this right? You just do something. And she wasn't going for this. It's her itch. She was going for like, and I just came out and like, she was like, I'm sorry. I was like, I was talking to you and I didn't tell you what I want. Yeah. I was like 3 months ago, I had a crisis, and I went to the grocery store and bought a box. And I was like, and then, like, you know, 2 weeks later, it was blocked. So when it threw out, it was just like, it was just And that's why I was like, I brought it back to the car and did it myself, and now I learned my lesson.
Although I will say, I go about every 6 months. I like sitting there and then I use shades because it's got a lot of protein. It's good there, and it's semi-permanent, and I can just wash it out. But you have to get that kind of hairdresser. She doesn't do color, but she'll go so, and I'm like, I have to get like 3 different colors I put in. It's never the same.
That's awesome. I also remember when I was used to we
Okay,
there was like engagement we had.
let's review that tutorial that we had this week. When a pulse comes into a boundary between two media, a slow media and a fast media, a medium, it splits, and some of the pulse goes through to the new medium, and some of it bounces back as a reflected pulse. Now, let's just agree up front that doesn't seem that important when you're dealing with one spring connected to another spring. I mean, how many times in your life have you had two springs connected together and sent a pulse and worried about what happened at the boundary? Not so much. But this phenomena happens all over in our everyday life. If you're setting up a stereo system, you want the impedance of one part of your stereo system to match the impedance of the others. And if you don't, if there's a mismatch, then the signal coming in is going to split. Some of it's going to reflect back and some will transmit in. If you have water and it's going from a region where it's deep to a place where it's shallow, if there's a cliff underwater, what you'll see is that the wave will come in and right at the boundary it will split. And some of the wave will go forward and some will bounce back. It's just everywhere in nature. If you've got a fast and a slow region brought together, you get this dividing. Now, here I have represented two springs. They're tied together. One of them's fast and one of them's slow. I had a pulse, an incident pulse, come in, hit the boundary and split. After that pulse split, I took this picture. Can you tell which spring is the fast one and which one's the slow one? Okay, the fast one's on the left. Now here's how you tell. One way to think of this process is that the incident pulse, the original pulse, I call the mother pulse. Okay? The mother pulse comes in and gives birth to twins. And in the process, unfortunately, dies. But the twins take off in both directions. Now, these are the twins. Those twins were born at midnight at that hospital right there, both of them. Okay? And they scurried off. And you can see that that twin got further away from the hospital than this one in the time between when they were born and when I took the picture. Okay? So that's going to be the fast spring, that's going to be the slow spring. Now, if I had these two springs, where this is a fat spring and this is a light spring, which of those would be the fast and which would be the slow?
Whichever one's
Yeah,
less dense.
yeah, the light one would be the fast one. Your gut tells you that. Now we can argue that either from an equation or from our common sense. If we use the equation for a pulse speed on a transverse medium, like a spring, it's going to be the tension divided by the mass density. Now these two springs are pulling on each other. Can the right one pull on the left one harder than the left one pulls back on the right one?
No.
No, it would violate Newton's third law, and then the universe would end. Okay? That's the most beautiful of all laws. And so whichever spring has the biggest mass density is going to have the smallest speed. Now another way of thinking of this is intuitively. If you think of these pulses passing from neighbor to neighbor, think of the heavy spring as a whole bunch of football players, the linemen standing up here. And we got to pass the pulse by lifting up our neighbor. Oh man, you're big. And then the other spring is made up of ballerinas. Okay? And it just goes really fast. Okay. Now, say I have a pulse like that coming in on the slow, and it hits that boundary. Will the transmitted pulse be on the same side or the opposite side in this case? Same. Is it the same side in this case, or is it the same side in every case? Every case, every stinking time. You never have to worry about that transmitted pulse. It will always be on the same side as the mother pulse that created it. Okay? Now, what about the width? Is it going to be the same width as the original pulse, or wider or narrower? Wider. Okay? The question is, why? Now, the second page of that tutorial dealt with the why. You represented a pulse by two pulses. One pulse that was at the beginning of the original pulse, one that was at the end. And you figured out why it had to stretch. I'm going to do it a different way here. I'm going to represent that pulse as a school bus. But not any school bus. This is a magic school bus. This school bus can stretch, it can shrink, it can be whatever length it needs to be. And it's driving on a really, really slow road, a dirt road that's all bumpy. And it gets to a boundary with a fast road of pavement. Now when it gets to that boundary, the front of the bus speeds up. But the back of the bus is still back there in the dirt, going slow. And so sure enough, it stretches out. Okay? Now if it's going the other way, the front of the bus hits the slow side first and slows down, and then you have the pulse shrinking. Okay. So it's going to be wider. Now folks, don't worry about the amplitude. The amplitude, how high it is above equilibrium, that's messy, that's challenging. Sometimes it's bigger than the original, sometimes it's smaller. All you can really say for sure about amplitude is the reflected that's on the same spring as the incident will always have a slightly smaller amplitude. But we'll never test you on amplitude, just width. Now, consider the reflected pulse. Is it going to come back on the same side or the opposite side in this case? The same side. Because when you're going from a heavy to a light, that's acting like a free end. And we found last week that a free end reflects back on the same side. Now if we came in on the light and hit the heavy, that would be like hitting a fixed end, and then it would invert. Okay, one more question. If that comes in like that, the reflected pulse has to be on the same side, meaning up, but which way will it be oriented? Like this or like that? This or that? Like that. And the reason is the leading edge has to lead. Okay, the leading edge is the first part that hits the boundary, turns around and goes the other way. Okay, the leading edge always leads. Now, let's look at this handout that I gave you. This is the way a lot of these questions are asked. A single pulse came in and created these children. Okay? The original pulse is gone. It's already split at the boundary. And when we took this picture, that's what we found. Now, we're told that one of the springs is steel and one is brass. And we're told that steel has a greater mass density. It's the fatty, heavy spring. So in this case, which of these springs is steel? Right? Yeah. So the fast one's on the left, and that means that the steel one's on the right. Okay? And that's because the pulse on the left has gotten further away from the boundary. Now, here's the next part of the question. Which is the reflected pulse? Did the original pulse come in from the left, or did it come in from... You know, folks, we got 2 minutes. I got a way cool demo here. Rather than work this problem to the end, we'll do that on Friday. Let's just turn off the lights. Okay. You don't have to go to sleep. Yeah. Okay. Whoa. Now, this wave machine with the long bars is clearly the slow machine. These are the football players. The ballerinas over here, that's the fast machine. You like my shirt? Now, I'm going to send a pulse on the slow side. It's going to hit the boundary. The first thing I'd like you to concentrate on is the reflected pulse. Forget about what transmits. Just look at the reflected pulse. It's going to be on the same side or the opposite? On the same. And it's on top. It comes back on top. Okay, with a little smaller amplitude. Now look at the transmitted pulse. Let me calm this down a little bit. Whoa, Nelly. Okay, not much there. Okay, the transmitted pulse is going to be wider. And sure enough, it's very wide. Okay, now let's send the pulse in on the other side. Look now at the transmitted pulse. You're going to see that it gets narrower. And it did. Okay? Now concentrate on the reflected pulse, and you'll see that it'll be on the opposite side because it's like hitting it fixed end. So it's going to come in on top and come back on the bottom. And sure enough, it did. Okay, folks, we're out of time. Let me turn on the lights before you move. Let's not work right now. Okay.